today's class. So first of all, let's see here. So announcements-wise, your first real homework, as it were, is due tomorrow evening. Remember that you do have some late days, but there are, what, 5 homeworks total? 4? 5. 5. So all the due dates are listed on the Google spreadsheet. It really is due tomorrow. Some people seem to think it was due today or Thursday. They're not correct, and I promise I haven't doctored that spreadsheet. I'm too lazy to do that anyway. Then your next homework will also go out tomorrow. So hopefully we've revised that or are in the process of doing that. And the next one will be on skinning, I believe, which is a fun thing that involves what we'll talk about today. So are there any questions procedurally about what's going on in this class? And your grades for your first homework are going to go out as soon as we can figure out how to make this learning module things, make them visible to you guys. So they're all graded. There's just like some button that none of us can find, so that makes them visible. Keep changing these things.
Yeah, were 0 points we gave you like a grade that would be what we would have given you?
Yeah. Yeah, please don't get an argument about your grade on homework 0, but rather ask for a clarification if you think there is something you didn't understand about how your thing was graded, because it doesn't count in this class. Oh. Any additional questions? How many of us have started the homework due tomorrow? Most of you. That's great. Okay. And the rest of you didn't raise your hand. I'm going to assume it's because you're looking down at your computer. Right. So today we're going to talk about coordinates and transformations. This is like the classic topic to cover in a computer graphics class, and it's one that should sound awfully familiar because all of you in theory have taken a linear algebra course. So today we're going to roughly follow the textbook by Stephen Gortler, although he develops a very complicated notational system that I think is a little pedantic. So at times I might get lazy and not follow, but I'll try to. And at any point, if you're wondering, like, am I not following or is Justin being lazy, feel free to stop me and I'll clarify. Okay? Right, and basically, rather than thinking about coordinates and transformations, really what we're talking about today is just bookkeeping in computer science. Your instructor happens to be minorly dyslexic, and I hate this topic because I can never remember, like, which side to multiply which matrix by, and so on. And so the fact that your instructor constantly gets confused by this might be a good indicator that you guys should be very careful when you do these computations. And it's not that like 3x3 linear algebra is that hard. It's just that it's easy to get these things subtly wrong, like do you multiply on the left or the right and so on. And I think a lot of the way that I see students kind of reason about this is just like, oh, I have to multiply a matrix, so I'll just stick it somewhere and figure it out later. That's not a good approach here. You guys should, every single time you do another step in one of these, you should think through, like, geometrically, what did I just do? Like, I have a point in this space, I just applied this thing, now it's a point in that space, right? And that's like a phrase that should go through your head over and over. Okay? So our basic task for today is to talk about hierarchical modeling. And so the high-level idea of hierarchical modeling is that in a typical scene, there are a lot of different coordinate systems. Right? There's the coordinate system of the camera, the scene, the car, the driver, maybe the arm of the driver inside of the car, and so on. And the reason for that is that it would be really weird to choose one origin and ask that everybody model your scene in terms of that one origin. Right? Like for instance, this guy's arm is maybe pivoting about his elbow, and describing that pivot about the center of the car wheel wouldn't make a whole lot of sense. Right? And so really what computer graphics systems were, at least circa maybe 5–10 years ago, now OpenGL has actually removed all of these features and made them, you code them yourself. It's just one giant stack keeping track of all of the different coordinate systems that you're in. Right? And the idea is that, like, well, while I model the human, maybe I'm in his coordinate system, and then while I model the arm inside of the human, I'm going to kind of move OpenGL's viewpoint to the arm, and then I'm going to move back to the human, and then back out to the car, and this kind of traversal happens up and down in the computer graphics pipe. So that's the kind of high-level story. Hopefully that makes sense. So that's what we'll talk about today, and then next time we'll talk about skinning. Oh, I'm realizing I didn't quite finish our last lecture. We'll get to it at some point. This thing is important. Right, and in our next lecture we'll kind of talk about averaging different coordinate systems for skinning, right? Where you can kind of view, you know, this part of my skin is attached to the upper part of my arm, this part is attached to the lower part, and then there's this kind of goofy stuff in between that's somehow affected by both rigidly moving parts, right? And how to combine that is its own challenge. So put it a simpler way, if you give you a scene like the one I show you on the screen and I ask you where the origin is, it's not totally clear, right? I think, probably in this scene, maybe I put it in the base of the rocks, maybe I put it in the corner of the image, who's to say? And of course, maybe this thing is really sitting inside of the Windows logo, in which case the origin probably changes, and that thing is sitting inside of space. And every time I model one of these scenes, I want to choose a different point 0, 0, 0, because of course the astronaut trying to model this blade of grass from like miles away is probably not the right way to go. Yeah? And so this is just an extreme way of putting a very simple observation, which is that rarely do we actually use absolute positions in real life. Right? And really, computer graphic systems are just built around this as the baseline assumption of everything that we do. Okay? So what we need to do in this class is be super careful about what our coordinate systems are. Okay, so today we'll talk a lot about points as just tuples of coordinates. In this class, I'm going to try to always use column vectors. If you're using row vectors, you're doing something wrong, or using a really old version of OpenGL. Really old OpenGL has all kinds of weird conventions. Like they had left-handed coordinate systems for a while, which was not a good thing. Right, and I'm a left-handed person. But in any event, the idea is that if I give you coordinates and I say, Sophie is sitting at point 1, 2, that is meaningless without understanding the origin, understanding what it means to be a displacement, and so on. Right? So for instance, it could be that red point in the red coordinate system, the blue one in that system. Which are easy to do. Okay. So today, we're going to try and distinguish between a lot of different types of objects. Points, which are locations, vectors, which we're going to think of as displacements, normals, which are like unit vectors, and coordinates, which are positions. So coordinates are kind of like the actual numbers that correspond to the geometric object, which is the plot. Yeah? And I think when you take linear algebra class, you kind of take all 4 of these objects and just think of them like this tuple here. In this class, we're going to try and distinguish a little bit because it's going to matter, right? And eventually, we're going to introduce a little bit of nonlinear linear algebra, right? We're going to talk about homogeneous coordinates. And we're going to see that if we do our bookkeeping just right, we're going to be able to do some sneaky things, like actually justify that when you subtract 2 points, you get a vector, and see that that happens mathematically. Okay? That's kind of our goal here. So first of all, continuing in the boring things that you've probably seen since pre-calculus class, one thing that's important to note is that, of course, points and vectors are not the same. We might write them as tuples, but they're not the same geometrically. Right? The 0 vector actually means something, right? It means no displacement, no velocity, whatever. The point 0 means nothing. It's just a convention. Right? And similarly, we can't add together 2 positions. The sum of Boston and New York is. I shudder to think what it is. Okay. Right. So put another way, because in this class we like to repeat everything 5 times before we move on to the next point. Essentially, if we talk about a moving car, the point would describe its location, and vectors would describe things like velocities and so on. And of course, translating your car would be like taking a point and adding a vector to it. Okay, so of course, if we're building everything up using linear algebra, then we have to talk not just about vectors, but also matrices. And in our class, matrices are actually going to take kind of 2 dual purposes when it comes to coordinates and transformations. For one, they're going to transform things. So for instance, maybe I want to render this table, but I'd like to render it sitting there, right? So then I can multiply its coordinates by some matrix and rotate the table. Or a kind of dual way of thinking about it is to change your coordinate system, right? So maybe I'm moving from describing this table in terms of some origin here to describing it in terms of the corner of the room. Right? And we'll see that obviously these 2 things are kind of dual of one another, right? I can do it either as I move this table, or I move myself, and the table is in my coordinate system. But it's important to realize, and in fact, in the graphics kind of pipeline, I would argue that these are actually somewhat different, right? That really, when you're modeling, there's some actions you take where you're really trying to displace an object, and there are other times where you're just trying to put something in a scene, and they're not necessarily the same. It's a little bit of philosophical. At the end of the day, by the way, mathematically, it's all that matters. In this class, I'm never going to test you on these goofy vocabulary words like, is this a displacement or a rotation? I don't care. We'll give you a task to do, and you can decide to express that whatever way you find intuitive. And indeed, that really is the way that the computer graphics world goes, right? So Something we'll learn later in this class is that OpenGL, this library that we're using for graphics, changed from what we call a fixed function pipeline to a variable one. And the idea was that old versions of OpenGL really were built on these stack of transformations, and they made a lot of assumptions about the geometry we see. Now OpenGL is just a library that's really good at drawing triangles, and anything else you want to do is on you. And the philosophy was that, who are we to determine exactly the right engineering decisions for your application? Okay, so our goals today are to define a coordinate system, talk about changing them and transforming objects, and the whole time we're going to keep a really careful notion of the difference between all of these different objects. And actually this last point, although I think verbally you've communicated it in algebra class in the past, you might not have notated it the careful way, and that'll be a slight kind of difference from what you've seen before. Okay? Alright, so let's get started. So, first of all, vector space. We'll start with a little bit of stuff from your algebra class. Remember that a vector space is a set of things that you can add together and multiply by scalars. Weirdly, the way that 837 is organized, you actually saw kind of an abstract vector space to start with, right? The space of polynomials. And now we're going to talk about the one that you're probably used to thinking about from algebra class, which is just vectors in R3. And there's one special element, which is the zero vector, and which corresponds, anytime you multiply anything by the scalar zero, you get the zero vector. And when you add it to anything, it doesn't change. So these are the basic axioms of being a vector space, and that's what we'll cover today. So, of course, in order to actually do calculations in a vector space, we need to use a basis. Hopefully all this stuff is review. So a basis is a collection of vectors that span your space, and are linearly independent, meaning I can't write any one of these guys in terms of the other ones. And the fact that it spans it means I can take anything in my vector space and write it as a linear combination of my basis. Right? In other words, there exists coefficient Ci such that V is the sum of the Pi's. Right? So for instance, the Bernstein polynomials were a basis for the cubic polynomials because any cubic polynomial could be written as a linear combination of those guys. Okay? So if we notate that, of course I think you guys are all used to the picture up here. You can see I put this cute little vector sign in front of the vectors today. Pretty soon we're going to have like tildes and bold things and capital letters and all that crazy stuff. And one way to think about a linear combination is this kind of a multiplication by a row and a column. You guys see that? So if I construct a matrix whose columns are B1, B2, and B3, and I multiply by these weights, C1, C2, and C3, organized in a column, right? Remember that matrix multiply goes like that? Yeah? So you get B1 times C1 plus B2 times C2 plus B3 times C3, which is exactly the linear combination you want. And of course, that gives us a little bit of shorthand, right? That allows us to write the expression down here, which is saying the vector V equals to the matrix B times C. And this is the first time where we're going to be a little pedantic about notation here. So for instance, formally, I haven't actually written B1, B2, B3 as like points or columns of numbers. This could be abstract objects, and this still kind of reads okay, right? I still just keep multiplying left, right, up, down. And so if I think of B as just some matrix whose columns are vectors, but I don't care how they're represented, right? Then I'm going to use bold-faced characters to actually talk about columns of numbers specifically, and arrows to be vectors. Do you guys see the pedantic difference here? That like you can think of these things as like displacements in 3D, like geometric objects, and these guys are actually numbers. This is pedantic because, of course, how do we typically represent these three guys is also using numbers, but that's beside it. Okay. Right, so everybody with me so far? This is our basic setup for today notationally? Great. Okay, so the next thing we need to do is transform these objects, and since we're in 3D, or in this case 2D, of course our transformations are pretty simple. They're shown across the top. And these are all the different linear things that you can do to your vector space. Right? Now remember that the actual definition of linearity is as follows. If I apply a linear operator L to the sum of two things, it's the same as summing L applied to those two things. And when I apply a linear operator L to a scalar multiple of V, we get the scalar multiple times L of V. This is the definition of linearity, not that it's given by a matrix. Yeah? In fact, if you take functional analysis, you'll start here and then you do all kinds of crazy stuff with it. Yeah? And of course, this implies that L of the 0 vector equals the 0 vector. Right? The proof of that looks a little bit vacuous, right? L of the 0 vector. Remember, the 0 vector is equal to the 0 vector times the scalar 0, right? And now I can apply that second property. And in a sense, it doesn't matter what this is, it's multiplied by 0, so it has to equal the 0 vector. Yeah? Kind of a goofy proof, but that's okay. Okay. And so we typically use this little arrow with the doodad on this left-hand side to kind of say that we're mapping from B to Ln. Right? That's how you read that. Okay. So let's throw out something that you guys probably already know, but maybe you've never thought about very explicitly. So let's say that I take a vector v, which is a linear combination on our basis, and I want a new expression for that. What can I do? Well, I know that L of v is equal to L of sum of ci bi. Right? That's just by definition. Right? And now, well, let's go back to the axioms that we have about a linear map. If we apply this first one, right, we see that that's equal to, this is the sum of I, the sum over I of L. Right? And now, if we apply the second axiom, of course, we get the sum of I, C, I. Okay. So, initially this seems really boring. We already kind of knew this from algebra class, right? But this is profound. Do you guys see what this expression is telling me? Like, all I've done is define a linear map in terms of these two relationships. But what this is telling me is that, in fact, if I know the action of L on just a set, a finite number of basis vectors B, then I actually know the action of L on any vector. Right? If you think about it that way, it's kind of cool, right? I give you two very simple relationships, and the fact that there exists a basis. And now we know, because I can write any v in that basis, that in effect, L is completely determined by a set of vectors, a finite set of them. Yeah. And so this is going to matter for us a little bit, because it's going to determine how we think about a linear map. Right? So again, essentially what we've shown is that we don't need L as a function. It's enough to just know n different vectors. Does that make sense? And so one way to think about that is that if I take a vector which is a linear combination of my basis, that's what we wrote before, and now I apply L to that vector, then really all I've done is written the same coefficients in a different basis. Yeah? And so that's effectively what we've talked about. Yeah? And so, right, so the trick in linear algebra is always that we kind of have turtles all the way down. Yeah? So in particular, let's say that L maps from one vector space into the same vector space. Okay? That's not necessarily true, right? Linearity could map from one vector space into a different one. But let's say that it maps into the same one. And let's say I take a basis B. What's the definition of the basis? Well, it's that any vector in that space can be written as a linear combination of the basis vectors. In particular, I could take, for example, B1, apply L to it, that's some other vector, and hence, it has its own coefficients in the B basis. You see this is a little sneaky? I apply my linear map to the basis vectors and I'm writing it in the basis again. So think about rotating 90 degrees, right? I started with the x-axis, now I'm going to say, I know it rotated 90 degrees, now it's 110 on the y-axis. But that's a statement where I took the output of the rotation and wrote it again in the xy coordinates, yeah? Okay. So if I do that, well, okay, so if I want to apply L of B1, L of B2, L of B3, and I compute these coefficients for each of those three vectors on the left-hand side, then what do I get? I get a matrix. And so in a sense, what is this telling me? This is just a very fancy way to talk about multiplication on the right. Yeah? And it's essentially saying that if I apply a linear map, it's the same thing as taking my basis matrix and right multiplying it. This is the first instance where your instructor is going to start to be dyslexic about this stuff. Okay. So we put everything together so far. Essentially, we can think of a linear map as kind of inserting a matrix between the basis on the left-hand side and the coefficients on the right. He goes right there. Yeah? In other words, we have this fancy notation. Cool. You can can see how this is basically the same as what you see in linear algebra class, but I'm trying to be really, really careful about where I stick these matrices rather than just always multiplying on the left, which I think is what you do in algebra class. Because really where you put them matters a lot, and geometrically is interpretable. So one of the nice things about matrix multiply is, of course, that it's associative, meaning that I could parenthesize this way, or I could parenthesize that way. Yeah? And actually that has a nice meaning geometrically, right? So I can sort of interpret this mapping up here in two different ways, right? If I parenthesize on the left, I can give it as transforming the basis, right? Instead of b, I now have b times m, but leaving my coefficients the same. Or I can go keeping the basis the same and changing the coefficient. And this is sort of the difference between left and right. Okay? And that's, of course, exactly the same duality that we started with the beginning of class today. Yeah, sneaky, huh? So what? So first of all, there are tons and tons of fast algorithms for linear algebra. Many of them are actually irrelevant for computer graphics. Like you might be familiar if you take an advanced theory class that there's all kinds of crazy algorithms for matrix multiply that are faster than n-cube time. But they are only faster than n-cube time for like really, really big n. Our n is like 4 here, or 3. You know? So typically you just type in the formula. but that aside, essentially this gives us a really convenient way to very explicitly keep track of our current basis, coordinate system, and so on. And really, when we talk about things like change of basis and so on, it's critical in computer graphics to get this right. Because, again, we're going to go from the world to the car to the arm to the hand and back out. And what's going to happen is every one of those is going to be matrix multiplied. And if you get one wrong, it's going to have a crazy global effect on the scene that you render, right? Because all of a sudden, everything else that you render is displaced the wrong way. Yeah? So the typical issues are remembering which things are M or M inverse and keeping track of what space you're in. And I keep warning you that, and then you're not listening to me and say, yeah, but I'm smart, and you're just making a goofy mistake. And I guarantee you, you're likely to get this wrong if you're home for the first time. Yeah? Okay. So my high-level advice for how to get it right is to think of a matrix as sort of a thing that takes in a vector and outputs another vector. Right? And so when you read expressions that are big products of lots of matrices, which we're about to do, you should kind of read it from right to left. Right? So I say, like, I take V, and then A outputs A times V. So I can think of, for example, A as the matrix that goes from car to hand. Right? So then A inverse is from hand to car. So you kind of think of, A, the things here and the car coordinate system, the things there are in the hand system. And literally, when I do this, oftentimes I'll kind of write little arrows telling me which space everything is in. Okay? Right. So we should talk about change of basis a little bit, and of course we've already done that, right, in the context of a linear function. And so one way to do that is if we have two bases A and B, just by definition of basis, we can always take one guy and write it in terms of the other. Right? And a different way of writing that is A equals B times M. Notice the right multiply here. By the way, if we think of these as vectors, the right multiply makes sense, right? Because it's kind of linearly combining vectors. And of course, assuming that these are bases, then this matrix M is invertible, so it's a way to go backwards. Yeah, just back. Okay. So let's say that I'm given a vector V in the B coordinates, and I like it in the A coordinates. How would I do that? Well, there are many ways to derive these kinds of formulas. The way that I typically do it is, okay, B we know is equal to B times C. I don't know how to write bold-faced letters, whatever. What I'd like is that this is, well, if I want to write in the A coordinate system, then I know that I have to write it as A times something, right? That's one way to reason about it. What's the easiest thing to do? Well, just cancel the A and put a B there. Yeah? And now you have this thing, if you group it that way, is of course the coordinates in the other system. So that's the usual kind of trick we can do. Right, so I guess here, oh gosh, I've already made the same mistake that I just told you not to. That we're thinking of these guys as vector spaces. Of course, I should never use A as a matrix, but rather the thing of coordinates that transfers from one to the other. That's my mistake. You see, this is a mistake one. I get 3 today, in case you're wondering. So a different way of putting it is B equal to A times M inverse. Yeah. So if I want, sorry, if I want an A there, one way to get it is to notice that it's right here. Yeah. is in A and L. I'm sorry, that was a stupid mistake. Is everybody with me so far, or did I just lose the whole room and one stupid shot? Cool. Great. Okay, so right, so that's our basic trick. You can see that even your instructor doesn't like being pedantic about like, well, this thing is really a thing that contains vectors, and this thing is a matrix of coefficients. This is really kind of a pedantic way to write stuff down, but I suppose for our first lecture we should be careful. Okay. Right, so so geometrically, of course, I think you guys have all seen pictures that look like this, maybe not with this ugly fish, but with some object or another. We know that linear transformations correspond to, well, which of these things? So, is the identity transformation linear?
Yes.
Thank you. How about uniform scale? Yeah. How about reflection? Translation?
Yes.
No. Right? Because think about applying L to the 0 vector. Right? We know that L applied to the 0 vector should get the 0 vector out. But here it didn't. Yeah? So in fact, it's really, really important to note, and although we kind of think about translation in linear algebra class, translation is not a linear operation. Right? So this example where I translate my T is sufficient to show. Why do you think that is? If we think really carefully, I mean, so far we've talked about vectors, but we haven't talked about points. Right? Translation doesn't make any sense unless you have points. You see that? So if we think of linear algebra as like a tool for dealing with vectors, so then really we shouldn't be able to do translation in that language. Okay, so now let's introduce some more geometry. After 10 seconds while your instructor leans out the door and asks his people to place what they're actually doing. Nope, just some gas leak out of the chemistry lab. Yeah, that's terrible. Okay, so let's talk about this. So, I think yeah, we'll keep that door closed and help us steadily in the class. Right, so a point is just a location in space. It's totally meaningful to add vectors to vectors, and it's totally meaningful to add vectors to points. Adding vectors to points is not meaningful, and I think we all kind of get the issue with this one. Okay. So here's going to be our slightly pedantic thing. In fact, just this morning I was editing somebody's graph proposal and they got this wrong. A linear space does not include points, it does not include translation, and affine space does. Right? This is the difference between an affine transformation and a linear one. Affine stuff translates and applies linear math. Linear things just apply linear math, so they can't translate. Okay? And these are extensions of vector spaces that essentially include an origin point. Although, again, I think we often muddle these things together in intro linear algebra class. Of course, we have a hammer. We should hit as many nails as we can with it. And in particular, if we've written a piece of code that can deal with matrices and vectors, maybe we try to reuse it here. So in particular, it turns out we can cheat just a tiny bit notationally and include translation, and that's what we're going to do here. It's also what typically is implemented in graphic systems, which is to say that now I'm going to make this funny matrix whose first 3 columns are your basis, and whose fourth column is some origin point. Notice we're now going to be even fancier and put a tilde over points. You see how I'm going to get this wrong? Because in math we don't bother putting any sign on dots. Okay. And what I'm going to do is I'm going to take my vectors of coefficients, and I'm going to just stick 1 on the end. And now this thing I claim is a point. Do you see that? Because it's vector plus vector plus vector plus a point. So I think it's important to make to note. Would like putting a 2 there make any sense? No, I can't scale a point. It doesn't make any sense. So it has to be a 1. This is a notational hack. Okay. So why do we do that? So let's say I take 2 points written as these coordinate column vectors, and I subtract them. What happens to the 4th element? What else be 1? I subtract 2 points written as coefficient, coefficient, coefficient 1. What's 1 minus 1, everybody?
0.
Okay. Yeah, I get a 0 there. And by convention, we're going to think of vectors as things with a 0 in the last component. And it turns out all of these relationships I keep repeating, like vector plus vector equals vector, end up working out, right? If I add two vectors together, it's going to be 0 plus 0 in the last element here. So that works out. Right? If I have a point plus a vector, that's an okay thing to do. If I try to add 2 points together, what happens? I get a 2 there, and that's against the rules. Notice if I took this whole thing and then divided it by 2, it would actually make sense, right? It's kind of like the midpoint between two places. And we're gonna formalize that in this one. Yep. So in other words, you know, what we've shown is if we take 2 points, we subtract them, we get a vector. If we add a vector to a point, we get another point. And so somehow this is a nice, elegant notation. Yeah.
So then if you subtract 2 points together, you get a 0 loss.
Which is a vector.
Yeah.
Which makes sense, right? Because that's the vector from one thing to the other. Yeah.
But then if you add 2 points together, does that not give the same directionality? Like, I guess, intuition.
No, points you cannot interpret as vectors, right? Because it doesn't, like, how would you draw it? There's no arrow.
Yeah, I was just curious because like subtraction is basically like you could just multiply negative 1 and 1 to addition. And so I thought maybe there was like some.
No,
like,
yeah. In
symmetry.
this class, you are not allowed to scale points. You can scale vectors by -1. Points you can't. We're going to, in reality, in the next lecture, we're going to relax this a little bit because we all know we can do certain tricks like this. Yeah. But here, if we're going to be really pedantic about it. Yeah. Okay. Right. So this is what we call an affine. So rather before we had a basis for a vector space. Now, if we want to talk about the kind of analogy of a basis for an affine space, we'll call it an affine frame. And this is just an origin plus a basis. Right? This is kind of what we're used to thinking about geometrically, right? Like there's some 0 point, and then there's a bunch of vectors pointing out of it which define our space. Yeah? And we can define any point in a space as the origin plus a displacement from the origin. This is just a careful linear algebra notation. Okay? And notice that we're going to keep our coefficients in a bold-face vector, which means it's explicitly the set of numbers. The b's can be anything you want. They can be polynomials, right? Abstractly. Okay. So here's our recap so far. Vectors can be written in a basis, and we have this nice change of basis formula that the instructor got wrong in this first try. That's my bad. We have points that can be expressed in a frame, which includes an origin, and we can also keep track of the frame using this cheap notation where it's taken up. Cool. And I think typically what you're used to from algebra class, one way to think about it is you just kind of omit this guy, and he's just implicit, right? And the difference here is that we're writing it explicitly. Okay. So affine transformations, unlike linear transformations, also contain translation, and let's see exactly how that works. Okay. So now, if I've taken a point in 3D, I've expressed it as a vector in R4, right? There's something 1, right? And so now I have the freedom to actually have a 4x4 matrix, which looks like this. And do you guys see what's going to happen if I multiply these things out? Let's say that I have a point and I insert a matrix here like that. Well, right. So let's take a look at the first 3 columns of our matrix vector product. I'm going to get vector plus vector plus vector plus 0. Otherwise, it's going to be a vector. Yeah. Similarly for the second and the third guy, we get vector, 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 vector plus vector plus vector point. So it's exactly just a change of frame instead of a change of basis. Make sense? And so the way to think about this is I'm applying a linear transformation to my space, and at the same time I'm moving my origin to some new origin, which is the old guy plus a vector. Cool. So let's write that out a little more carefully. So this is a way to write a valid frame. And so in particular, now let's talk about linear maps. So first of all, let's say that I have a linear map of my basis, but I want to leave my origin alone. How do I express that as a 4x4 matrix? Stuff requires a little bit of like cranking in your head, right? Yes?
You just add row of zeros at the bottom?
Exactly. So if you kind of want to leave your origin alone, right? So you have your basis, which satisfies this relationship here. So one way to think about this is that then I have my matrix M. 0, 0, 0, 0, 0, 0, right? It's really 3 by 3. And then a 1 there because you want to leave your origin. So really the kind of upper left 3 by 3 block of these 4 by 4 matrices can be kind of understood as the linear part, like what you're doing to your basis. And that's what you see here. Similarly, let's say that I want to translate my origin but leave my basis alone. Then what would my matrix look like? First of all, what should be the kind of upper left block here? I want to leave the basis alone. What matrix leaves something? Identity. Yeah. Identity in this block. I don't want to mess with it. I have to have a 1 there, so we get a 1 output. And think about it, you want to put your translation vector here, right? Because remember that when you multiply this together, this just gets multiplied by 1 in that sum. Okay? It's kind of like adding t to the last column. So a different way of putting it is as follows. Yeah, exactly here. Right. So you have identity 0, 0, 0, 1 on the bottom, and your translation. Does everybody get the game here? Yeah. So this is a sneaky way to include translation and linear maps all in the same thing. And if you struggle to think about it like I do, typically what I do is kind of say like first I'm going to do the linear map, and then I'm going to translate, or vice versa, and separate it into 2 matrices and then multiply them together. The great thing is you can do that by hand on paper and then type in the final formula in your code to be efficient, but whatever helps you think about it is fine. Yeah? Okay. Right. And so in general, if you want to have a whole, a new affine expression, then I have the origin plus a translation vector here, and I have a linear map here. I can do that by putting all these things together into one giant matrix. So this is why 4 by 4 matrices appear all over the place in graphics world. It's just a sneaky way to include translation in what you're doing. Yeah, that's all it's called. Okay, so let's continue to play some fun games. So like we talked about before, if we take 2 points and we subtract them, then of course what you get is a 0, which makes sense. If we add a point to a vector, then we get another point. That's what we talked about before. And in particular, now let's say that I have a vector in this 4 by 4 notation, which I can do by having these 3 coordinates and a 0. Notice what happens when I multiply. I get like this guy times this guy, this guy times this guy, this guy, and then 0, right? So in effect, when I apply our matrix to a vector rather than a point, it just ignores that 4th line. Yeah. This is all just different ways of understanding the different blocks of this matrix. And so far, we've left everything here 0, 0, 0. We'll see later that it's convenient to mess with that, but we'll come back to that later. So this is our basic way of translating from one coordinate system to another. Or remember, if we translate the other way, we can think of it as moving all the points on an object to another location in the original basis. These are dual views of the same point. But of course, in typical graphics system, we don't just have one of these things. We have many different frames that we have to deal with. Right? And so, for instance, maybe I want to rotate the wheel of the moving car. So one way to do that would be to start at the world frame, go to the car frame, go to the wheel frame, rotate the wheel, and then go back out. Right? And that's a very typical thing to do. And of course, if you really want to do that carefully, you end up with a diagram like what I've drawn you here. And this, I guarantee you, is the kind of thing that everybody has to do at least once in their life. Yeah? So here, for instance, if I think of A as going from car to world, right? The one thing I might do, if I want to rotate my car, go from the car to the world, and transform the car, and then go back to the car coordinate system. For instance, if I want to draw this stuff on the inside. And notice the way that I've thought about this here, right? That I'm saying like, A is the thing that goes from car to world, which means that it left multiplies. So when I put the inverse, it goes from world to car. And I really recommend that you guys think through things in this sort of chain of like, now I'm in this system, now I've done this, now I'm in that system, now I do that. And that's the best way to reason through this stuff. And of course, what that gives you is really machinery for combining transformations together. So for instance, maybe a scale, I want a 2 by 2 square at point 3, 1 here. And I start with a unit square, so the first thing that I do is scale it, right, to be 2 times as big. Does that involve translation? No. So the scaling looks like this, right? The third element gets left alone. We're in the plane here, so these are 3 by 3 instead of 4 by 4. And then I want to translate, and we know that translation you just put in the right-hand column here. And the product of these 2 matrices, notice I've gone right to left, even though I've drawn this diagram left to right. This is the #1 point of confusion here. And when I multiply them together, I get a matrix that does both of these things at the same time. Yes?
So, just to get like some sort of visual understanding, what would have happened, or what would visually happen if you had swapped those two?
Great question. Here you go. So, right. So to repeat our colleague's question here, I could have scaled and then translated, or translated and then scaled. And what I want to impress upon you guys is that these are not the same. Yeah. In particular here, I scaled and then I translated, and notice it ended up at the point 3,1. Here, I translated to 3,1 and then I scaled, but because I scaled, the 3,1 also multiplies by 2. Yeah. So that's the difference. Okay. And just in general, matrix multiplication is not commutative, guys. And that's why I'm going through this painstaking process of really being careful about where I place it in my expression and understanding geometrically what that tells me about life. Okay. And of course, algebraically, if you just do those 2 matrix products, notice that here the translation on the left, scales on the right. Here the scales on the left, translation on the right. You just multiply them out, you'll see that they're not. Okay. Excellent. So this is basically just a really careful way to encode kind of what we already knew from pre-calculus class. So now let's step it up just a tiny bit and think about things like cameras, which are going to matter when we do rendering. Okay. And this is going to require a piece of machinery called homogeneous coordinates. Out of curiosity, how many of you guys have encountered these things before? How many of you have heard of them in a math class? Yeah, there's some fun topology. Okay, so right, so typically that 4th coordinate isn't just going to be a 1; it's going to be all kinds of useful things. And the basic reason why is kind of encodes something that we all know from real life. So if you guys walk around the corner, you see those train tracks that go up into North Cambridge. Right? You stand right in the middle when there's not a train anywhere nearby. You look at the train tracks. What do you notice? They're parallel lines beneath your feet, but of course visually they kind of converge together. Yeah, and the reason for that is that when you think about your eye, really there's some cone that's coming out of it that's widening, which is all the stuff that you can see. Right? And when you go 2 times farther out, you have a 2 times wider view. Yeah? And somehow linear algebra hasn't captured the fact that you have this kind of weird shape in your viewing system, which is getting kind of stretched out into the square, which is the image that you're rendering. Can you see that? Like when I think about a rendered image of a scene like that, really I've placed your eyeball here, and I'm kind of drawing a cone that looks like that, and everything in this cone is visible. Right? And so I need some way of translating from like a weird cone shape to a square where every pixel is what you render. Although here, these pixels are not parallel. And that's essentially the train track effect that you see. And so that's the math that we're going to develop, because of course that's the last calculation that all graphic systems have to do over and over and over and over and over again. Yeah? Okay, so let's talk a little bit of math. So, the homogeneous coordinate system, unsurprisingly, given what we've already done so far, is going to be, if you want the projective plane, or the homogeneous plane, is going to be 3 coordinates. So in general, you add 1 extra guy beyond the dimension of your space. So the homogeneous plane is the set of all points x, y, w, where we say that x, y, and w, and cx, cy, cw are the same for any non-zero c. Okay? So let's do a tiny bit of arithmetic here. So suppose that you have a point x, y on the plane. We want to convert that point to homogeneous coordinates. Can anybody give me the coordinates of that point? I know you can. You know, my mom was in the last lecture here, and even she was like, these MIT kids just never talk. They don't answer questions. No? How can I write x, y in homogeneous coordinates? Remember, look back at the previous slide. It's all points x, y, w, where any uniform scaling is using the same thing. So one simple way to do it is probably somewhat by convention, like x, y, and 1. Yeah? This is a point, right? This is looking kind of familiar given the first part of the picture. Can somebody give me a different expression of x, y in homogeneous coordinate? Yes?
2x, 2y, 2.
Yeah! 2x, 2y, 2. Is the name of the game? These are equal in projective space. Okay? How about the third one? I know you all can answer it. Seriously, I'm just doing this to like keep you like somewhat awake and it's making it worse. Yeah?
Minus x minus y.
Thank you.
Minus y minus 1.
Yeah, minus x, minus y, minus y. All both scaling and sign are perfectly free data. 0, 0, 0 is not considered the same. So now, suppose I take 1, 5, 1. I want to convert it to a point in space. How are we going to do that? Emily, how are we going to do that? Just that space is not in homogeneous coordinates. So remember, if I went from x, comma, y, comma, 1, or from xy to xy, 1, if I have xy, 1, then the point in...
Want it to be not homogeneous?
Yeah.
Or just be 1?
Yeah! You just lop off that 1. Exactly. How about 12 minus 6, 3? How could I convert that to inhomogeneous coordinates? 4 minus 2, right? I have to divide by the 3 first. You put a 1 there, and then read off the coordinates. And I'll let you do the third one. Yes?
Why did you choose the 1 in the first place?
That's by convention.
Okay.
Okay. Right, so that's the name of the game in homogeneous coordinates. I just stick a 1 at the end of my coordinate, and I add a convention that if I have some scaling in this vector, I don't care. Okay? And that's going to be useful to deal with the scaling that has to do with your eye. Yeah? And similarly, when we deal with matrices, we're going to add an additional row here. Right? We've already seen one example of that, specifically where the last row is 0, 0, 1. Okay? By the way, where do things get a little funky? Well, what if I put a 0 here? Is that equivalent to a point? No. No matter how I scale that vector, this thing will stay 0. Right? Whereas points, we kind of by convention put a 1 there. Yeah? And so somehow this space is actually slightly different from the plane. Do you see that? I've actually attached to the plane a set of points with a 0 on the end that I can't somehow achieve in my normal coordinate system. It's the beginning of some interesting ideas that are called points at infinity. Yeah? So what's one way to justify that? So let's say that I have a point Cx, Ci, Cy. Right? And I take C to infinity. Of course, this point is the same as what? And 1 over c, what does that approach as c goes to infinity? 0, yeah? So somehow what this is saying is, if I take a point and I just keep walking farther and farther and farther from the origin, that point eventually approaches this thing we call a point at infinity, which is where you put the 0 coordinate. Yeah? And really, you can think of this as kind of like a direction in the plane. We can see that this is kind of notationally convenient later when we want to talk about like kind of things in a scene that are so far away that like you don't want to place them; they're just like sitting in the background. You can think of them sitting at points at infinity. One thing that's worth noting is, what if I went in this direction? I reached the same point at infinity. Do you see that? Because x, y, 0 and minus x minus y 0 are considered equivalent in this world. If you're a mathematician, you should go like, what? And roughly, what's going on here is you're taking the plane and kind of close it like a piece of wrapping paper. If you want a really weird mind bender, I'll let you think about what happens there. It actually kind of takes the plane and turns it into a different topology. Like it's connected differently. Right? Because it's sort of saying, if I keep walking this way, I can kind of come back around the other side. Yeah. Anyway, this is philosophically an interesting point. If you like this kind of stuff, you should look at the stereographic projection of the sphere, and you'll see roughly what's going on. Okay, but anyway, that's a fun geometry picture. But in our case, why do we care about homogeneous coordinates? Well, continuing with this ugly fish here, this picture sort of gives away the story, right? Which is, we can kind of think of W like your depth coordinate, right? And your bigger your depth coordinate is, the wider your field of view. So in other words, if you think of W equals 1 as kind of where your computer screen is sitting, then when W equals 2, your coordinates are 2 times as wide. Right? So what are you going to do? You're going to divide by 2 to put it back on your screen. Yeah? And so that's the basic idea here in using projective geometry, is to encode perspective, right? So, for example, in one dimension here, we're just going to, by convention, and this is a convention, we're going to place our computer screen at the z equals 1 coordinate, right? And now we have a way of converting any point on the plane to a point, in this case, on your one-dimensional computer screen, by just dividing by that last coordinate. And so in other words, it takes the frustum, right? This is that like weird shape of stuff that is visible from your camera, and transforms it from this weird shape into a rectangle of pixels and all those straight out. Does this trick make sense to you guys? Cool. All right. And so one way to view that is you just added a delta. Okay. And so a different way of saying that is, in this case, if I just made our W coordinate the thing that I want to divide by, I put it there. And the reason why this is kind of convenient is that, for one thing, historically in computer graphics, division was more expensive. And so it was something that you want to save for the end. Like you want to do as few divisions as possible. Right? There are going to be a lot of calculations that we can do up to scale and avoid dividing it all until the very last step. And the other one is that simply you can't express certain camera relationships without some trick like this. Okay? So you could have done this all algebraically, right? You didn't need to write it in this notation. You could have divided by z everywhere, but that would get really cumbersome really fast. Okay. Great. So one way to get two-dimensional perspective in this case would be to take your z coordinate and just kind of copy it into the third guy. Right? This is a case where you have, instead of 0, 0, 1, you have a different. That makes sense. So this is just a sneaky visualization. And really the way to think about it, put another way, is if you have your z coordinate here, you divide it back out, and of course it places things in. Okay? And so the real showpiece of this kind of a trick is to implement perspective on the computer, which of course is something we all care about. I thought for fun we can highlight one kind of advanced example that's a research paper that you guys are all now equipped to read and page through. It's something called phototourism. At this point, it's probably a little out of date given some of the more recent machine learning techniques. The idea here is I have some common scene, like this is some location in Italy, in the middle of the city somewhere. There's so many people that are taking different photographs of this thing that I can kind of reconstruct the scene, right? All these photographs have lots of different points in common. And so I get some relative motion between one photo and the other, right? And so a very classical problem in computer vision is to, given a bunch of photos in a scene, maybe you try to reconstruct 3D geometry. The cool thing that these folks propose is rather than doing that, I just want a nice user interface for viewing your photographs. Right? Because chances are in your 3D scene, you'll never quite cover all of the points that you want to see. There must be some stuff that's not visible. But at least like a nice transformation from one image to another. It's kind of a sneaky trick. And so the way they do this is they establish the correspondences between the different images. So in other words, like there are two different photos of the same fountain, and this point in this image is the same at that point in that image. And if you have enough of those, then that can actually constrain the matrix M to the point where you can compute it. Yeah? So once they do that, they solve one problem which is called structure from motion. If you like this kind of stuff, I encourage you to take Bill Freeman's class in computer vision, which basically recovers these transformation matrices from one photo to another. And the end result is ridiculously cool. So let's watch the video. This is Supergraph from 2006. You can see it's 2006. Let's unmute the audio.
How can we organize such large photo collections in a more intuitive way? In this project, we present a novel system for registering large sets of photos and exploring them in a 3D browser. Our system discovers the relative positions of the cameras used to take each photograph, situates the photos in 3D space, and provides intuitive controls for exploring the scene and finding interesting photographs. Our system takes a collection of photos of the same scene as input. We first find key points in each of the input images, then match key points between each pair of images. Next, we run an iterative bundle adjustment procedure to estimate the parameters of each camera and the positions of the observed 3D points. Once the photos have been registered, they can be browsed using our photo exploration interface. Our system provides standard controls for moving around a 3D scene. In addition, when the user selects a photograph, the virtual camera is smoothly brought into alignment with that photo. Information about the photograph appears in the information pane on the left. Our system provides several intuitive ways to select new photos. One is to select an object. The user can highlight a region of the current photo, and the system automatically finds a good photo of the selection, and smoothly moves the virtual camera to the new photo. During transitions, we use a simple plane-based morph to provide context as the camera moves. A thumbnail pane along the bottom of the screen shows other photos of the selected object. When the user moves the mouse over a thumbnail, that photo is displayed in the main view, projected onto a planar approximation to the selected object. Here, the user selects a thumbnail to see a different view of the statue. We also provide tools for viewing the scene at different scales. The user can step back from the scene with the Zoom Out tool. This finds photos that display a larger area of the scene. The Show Me Similar Images tool finds images of the scene with scale and orientation similar to that of the current photo.
In the system, it's actually all it's doing is applying the techniques that we just talked about, these homogeneous transformations to the photographs, and then just kind of displaying them as little billboards on the right angle. And then when you move your camera, it's just moving these little billboards along. So you guys are all equipped by the end of today's lecture to implement the user interface. It's really, like, incredibly clever in that sense. So we have 10 remaining minutes. So in our remaining minutes, let's finish up our previous lecture. So let's all on coordinates and transformations. Essentially, the message you should get out of that piece of what we're talking about is you should be extremely careful with bookkeepings, right? And that it's really tricky to get this stuff right. Right. So now let's go back to our old story, which was subdivision. Yep. Right. Okay. So remember the basic technique that we talked about at subdivision? I know this is like now for something completely different, but I already didn't quite finish last time. I want to make sure we hit coordinates so that you're well equipped for your homework. Remember the idea of a subdivision scheme. The idea is that I take some piece of geometry, and now I want to go from that geometry to a more detailed one by introducing more elements like triangles or rectangles. Yeah. And so, for instance, last time we talked about the loop subdivision scheme. So we take two adjacent triangles like this. We inserted new points. This is a topological change. In other words, I've told you how to change the connectivity, but I haven't told you how to place these vertices, right? And one thing you see is you typically get valence 6 points. But in any event, by kind of very carefully choosing weighted averages of your neighbor, what you get is a rule that if you keep iteratively applying it to a piece of 3D geometry, what you get out is a nice smooth object instead. Right? And so the reason why we kind of like this in graphics is that the points here are relatively easy to control, by user interface, and behind the scenes they're controlling a nice smooth shape. That's what gets rendered. Yeah. Okay, so the one last thing that we didn't quite hit last time is a technique that I think is worth being familiar with, at least from a high level, because it's very popular in graphics. You might as well know what's going on. It's called Capel-Clark subdivision. Capel is now the CTO or something at Pixar. So the idea of Capel-Clark is that sometimes we have meshes which are not just triangulated, but also have things like quads, right? This is actually very common. So artists tend to like to lay out quads very carefully, especially on faces, because, well, grids are useful. Yeah? And so here, the idea is that you need to be a little more sneaky to have that subdivision rule be just right. Yeah? So in Capel-Clark, it happens in a few steps, right? So the first thing to do is inside of every face, that's like one cycle that contains nothing else, we're going to insert a point right in the middle, call that a face point. And on every edge, we're going to insert a point in the middle of those. And how do you think we're going to make new connectivity? Kind of a hub and spoke thing, right? So here I'm going to just draw a spoke outward from each point to each of its neighbors, right? And the reason to do that is, like, at the end of the day, obviously we don't care if we get triangles or quads or not. And this is just the simplest way to subdivide something so that now it has some new points to look at. Yeah. And this is our new connectivity. And then in the subdivision rule, you have to place a bunch of different points, right? And so the way that you do that is in a few steps. To place this new face point here, you make it the average of its neighboring vertices. Then you move the edge point as the average of the old and new neighbors. So these two guys and these two guys is this one here. And then finally, you will do a little bit more work on the old points, like this guy in the upper right, depending on his variance. At the end of the day, I don't expect you guys to remember all these things. But the basic strategy here is that you need two ingredients to make a subdivision rule work, right? You need one thing which says, where am I going to place these new vertices topologically? And another which says, where do I place these vertices in terms of the old guys, right? And these different subdivision rules are just different ways of taking weighted averages of stuff nearby in a way that makes sense. Yeah? And so at the end of the day, Campbell-Clark subdivision, for instance, this is a little hard to see. Has the nice property, which if I were mean, I would make you guys derive on paper, that essentially shows that you can prove that what happens in the limit as you subdivide this thing using this rule is you actually recover a cubic B-spline surface, which is exactly what we talked about at the beginning of a couple lectures ago. And so really, that's where all of these little averaging rules come from, is just by using the Ducastle-Joe algorithm very carefully. And so the basic advantages here are the subdivision allows you to have arbitrary topology. Like it's easy to model a donut. That sounds goofy, but remember when we talked about these bicubic patches, it would be kind of tough because you'd have to cover your surface with all these little patches. Here, we want a bunny, you make a bunny. Yeah? So it's much simpler. And kind of by definition, you get something smooth. And it's stable, it's easy to code. There's some disadvantages, which is that it's a little bit hard to really understand this surface as a function of those points. And so if you want to do really careful control over the geometry of this guy, then just moving around control points might be kind of hard thing to do. And of course you can mix and match all of the techniques that we talked about in that lecture. So for instance here, we have a subdivision surface, which is using Campbell-Clark, and then on top of that we added a displacement map, right, which is to take the surface and just move it along the normal, and you can see you get extremely detailed on the surface. Any questions about that procedure? It's a pretty cool looking stuff. All using pretty basic machinery. Yeah.
So like Blender's like subdivide surfaces all like that.
I believe Blender gives you the option to use Campbell-Clark, Loop, and several other rules. There are a bunch of square root of 3. So, yeah, if you take a CAGD class, you can do these for entire semester different precisions. Okay. So in your homework, which I guess is due tomorrow, of course. Essentially, you're doing some very, very simple procedural geometry, and you can flip back in these slides and see some information about what you're doing. So essentially, we've asked you to do much simpler stuff than what you've seen in this lecture, right? So for instance, you first draw the profile of some shape, and then you sweep it around the curve. And in case you didn't find it before, there are some hints on how to do that here, although your assignment also well. One kind of last thing to note is that, of course, there are many different ways to model geometry in the graphic system. We're about to move away from this part of our class. And so another popular one is to talk about implicit surfaces, where you write it as like a level set, like the zero set of some function. Guys, I still got another 5 minutes, for heaven's sake. So, for instance, this is useful for sources that are undergoing, changing topology. So I want to take these two blobs and merge them together by moving them close to each other. As you can imagine, as a triangular mesh operation, this is a huge pain in the tuchus, right? But as a parametric thing, it's not so bad, right? Maybe I have a Gaussian and a Gaussian here, and I just add them together. When I move them close enough together, the level set just kind of merges. Right? And so for these graphics applications where things split and merge together a lot, that's where you tend to see implicit surfaces. So in particular, talking about fluid simulation is a great example where we'll see that later in this course. And so really, the nice thing is it's very efficient to check the inside, the outside, and do Boolean algebra, that kind of stuff. But of course, it's hard to just render the surface at the end of the day. And you still have to extract a mesh, and that's a tricky thing. And beyond that, there are all kinds of cool ways people do geometry. So for instance, something called a point surface, which is exactly what it sounds like, just a big collection of points and little tangent planes. I think these are kind of gone out of fashion because you need a lot of points to cover a surface and render it in a good way. But there's some interesting math for how to render these things. So now, with that, we're done for the day. And I will see you guys, let's see, today's Tuesday. So see you on Thursday. Don't forget your homework's due tomorrow.
Yeah.
I drew for you on board.
Oh, that's probably what you wanted to do in my room. I forgot to text him that. Maybe I'll just be
That's where
Wait, are you?
You're right.
Oh, that's so
running a transformation in a different frame. That's all that's
So the whole story is just you should be careful.
What are you actually subtracting?
Great. Did you take this today? Then you should be all set. Your original class. Oh, okay.
Because I remember we were at
Have you read it like you had this class somewhere?
I like it now.
Okay.
It was one day where like
Yeah, so follow up with me tomorrow. So if you added it now, I should get the things on how this works. So follow up with me tomorrow and make sure that you added before they start grading your stuff.
sounds good.
Oh, yes, door, and then you have to, yeah, convert it.
Okay.
But the reason
Sure, have a good day.
get mine, so when we get mine, take this one from the basis. And once you get here, you do like, you already lost them.
Yeah. I see. And like, so, like, same stream has this like, smooth, like it can convert things to like
Yes.
different types.
Yeah,
It would be nice to use.
yeah, I think you can't do that here.
Segmented.
Like you could, yeah, I suppose.
It's delimiting on like different things.
The easiest way to do this one is called, but basically what you give it a format string and it automatically parses it for you. So you could do something like
Okay, so I give it like
this format string. And then it'll automatically, it is a reverse case.
and then I do like
Yeah.
okay. Nice, okay, sweet.
Okay, so basically I have a script that,
Thanks.
yeah. Basically, you give it a text model with the answers, and then it writes out this CSV that should be able to upload to the project, but
Multiple choice was like, okay, I can't remember what the letters mean, but I know like, the different orders.
Yeah, too bad we changed
He's
it.
not gonna flip the order.
yeah. So it should get like username and.
Thanks. See ya.
I'm not sure why this is not. Oh, I guess it. It was,
running session. Our
Well, I
only
think
dance
there's
one.
something on the.
Someone else dropped the
There's no
dance. I'm really
documentation
down
on
to like
what,
20 people. For real?
what.
I mean, okay, everyone
On
here
one
really
hand,
good
I'm not
staging.
complaining, but on the other hand, it's kind of like, what's happening?
Okay, bye.
So fine.
I don't know, I like this song. It's not a lot of fun for the slow
Slow angst.
It's not even that angst, I just like it.
It's not
It's
what.
pretty angst.
It's pretty angst.
Wait, look into the lyrics. It's slightly hopeful, I'm hopeful towards the end.
That's probably what steered the angsty people away. Like it's too angsty for the not angsty.
And not
Yeah, so-
nice.
Error, you are importing a file that's not important. Didn't know like, didn't know documentation about.
Like, I don't know if you need to like download like to all assignments or just to do every single assignment at once.
I don't think so. I think it's a way for you to create assignments
Is it? Okay.
with the results.
Oh, so do I need to approve something? Is that what's going on?
Oh, yeah, so I'm not exactly sure what's going on, but like, if I hit, say, approve all grades,
Yeah.
then it says that, you know, Sophia Russo does not have the authority to approve an overall grade for grade though.
Okay, wait, let's see. Great.
There's like a tab, there's the assignments tab and the students tab. If the students tab, you're approved assignments.
Create assignments. Okay. I guess the easiest way is just to download. You have to create it on here and download it and then copy. Results. So at least they're alphabetical, but they're alphabetical by name.
You think it's smart enough to figure it out?
No idea.
Permission. Oh, permissions. TAs can approve assignment grades. There you go, now try.
Okay.
Okay.
Oh, now it is not. There we go, approve all grades. Okay. There we go, all set. Thank you.
Okay.
You might just want to check to see if you actually have this button now.
Yes, I tried. I'd probably check this to prove this correct.
Yeah. I don't know if this is a good time, but someone said that she wasn't able to submit in time. I figure because it's the first year of quiz, it's probably fine.
Oh yeah, there's some student who like to click submit for some reason.
Yeah. I give them plenty of time to hit submit after.
No, yeah, no, I don't think it's your fault. I think the students are just stupid.
Yeah.
Or she was